nearly 15 billion miles from Earth, farther than any human-made object has ever traveled. A 48-year-old machine is dying, its power fading, its systems shutting down one by one. But in what may be its final transmissions, it sent back something that made scientists freeze. Data from a place no probe was ever meant to reach. A barrier at the edge of our solar system. A wall of fire burning at 90,000 degrees Fahrenheit, hot enough to vaporize steel in seconds. Yet somehow, this fragile spacecraft crossed it and survived. If you want to know what it found on the other side, hit that like button and subscribe. Take a breath. We're about to cross into the unknown. Imagine standing at the edge of a cliff, looking out into darkness. Now imagine that darkness is on fire. That's exactly what Voyager 1 encountered in 2012 when it crossed the heliopause, the true boundary of our solar system. Scientists call it the Wall of Fire, but that name barely captures what this region actually is. The name barely captures reality. A zone where temperatures spike to levels that would vaporize any known material in seconds. We're talking about 30,000 to 50,000 Kelvin. In Fahrenheit, that's somewhere between 54,000 and 90,000 degrees. To put that in perspective, the surface of our parent star sits at about 10,000 degrees Fahrenheit. The Wall of Fire is 9 times hotter. It's hotter than the surface of many stars in our galaxy. Hotter than anything we can create on Earth except in particle accelerators and nuclear reactions. When Voyager 1's instruments first detected this temperature spike, the space agency scientists thought something was wrong. They ran diagnostics. They checked the data 3 times. Everything kept coming back the same. The temperature readings were real. The probe had entered a region of space that, by all logic, should have melted it into cosmic dust. But here's what made it stranger. Voyager 1 didn't just survive. It kept transmitting. Its cameras kept working. Its instruments kept recording. It sailed right through this inferno, like it was nothing more than a warm breeze. The reason lies in one of the most counterintuitive facts about space. Temperature and heat are not the same thing. The particles in the Wall of Fire are moving at incredible speeds, which gives them extremely high temperatures. But space at this distance is so empty, so devoid of matter, that there simply aren't enough particles to transfer that heat to the spacecraft. Think of it like this. If you put your hand in an oven at 400 degrees, you'll get burned immediately. But if you put your hand in boiling water at 212 degrees, you'll also get burned, even though it's cooler. Why? Because water has more particles to transfer heat than air does. In the Wall of Fire, there are so few particles that even though they're superheated, they barely touch the probe at all. Voyager 1 recorded these temperatures for months as it crossed through the boundary zone. Then, just as mysteriously as it began, the temperature dropped. The wall was behind it. The probe had entered true interstellar space. 6 years later, in 2018, Voyager 2 followed. It hit the same wall, same temperatures, same impossible conditions. But it crossed at a different location, and the data it sent back revealed something even stranger about the shape and nature of this cosmic barrier. What causes this Wall of Fire? Why does it exist at all? And what does it tell us about the edge of our solar system? The answer begins with understanding what the heliopause actually is. Our parent star creates a bubble, not a visible one, a magnetic bubble made of charged particles that flows out in all directions at nearly 1 million miles per hour. Scientists call this flow the solar wind. You might think the solar wind would just keep going forever, spreading out into infinity, but it doesn't. Eventually, it hits something, the interstellar medium, the stuff between stars. Gas, dust, and particles from other star systems, all moving through space in their own directions with their own momentum. When the solar wind crashes into the interstellar medium, it creates a boundary. That boundary is the heliopause. It's the point where the outward pressure from our star balances perfectly with the inward pressure from the galaxy. Like two armies meeting on a battlefield, neither able to push the other back. The heliopause sits about 11 billion miles from our parent star. That's roughly 3 times the distance to Pluto. To give you a sense of scale, if Earth were the size of a marble, the heliopause would be more than a mile away. The space agency knew the heliopause had to exist. Mathematically, it made sense. The solar wind couldn't blow forever, but until Voyager 1 crossed it in 2012, no one had actually measured it. No probe had ever reached it. We had theories, models, predictions, but no proof. When Voyager 1 finally arrived, it didn't just confirm the heliopause existed. It revealed that this boundary is far more complex and dynamic than anyone imagined. The heliopause isn't static, it moves, it breathes. The solar wind isn't constant, it fluctuates based on solar activity. During periods of high solar activity, when our star is throwing off more particles and energy, the heliopause expands outward. During quiet periods, it contracts inward. It pulses like a living thing, expanding and contracting over cycles that can take years or even decades. Scientists compare it to the bow shock of a boat. When a boat moves through water, it creates a wave at its front where the boat's momentum meets the resistance of the water. That wave is called a bow shock, and it marks the boundary between the undisturbed water ahead and the turbulent water behind. Our entire solar system is moving through space at about 43,000 miles per hour. As it plows through the interstellar medium, it creates its own bow shock. The heliopause is part of that shock system. But the heliopause isn't just a line, it's a region, a transition zone where solar particles and interstellar particles mix and collide. And in that collision, something extraordinary happens. The particles heat up, dramatically, violently. They accelerate to near light speeds. They ionize. They create a churning, invisible maelstrom of energy that exists nowhere else in our solar system. That maelstrom is the wall of fire, and it's far more dangerous than anyone realized. Voyager 1 wasn't designed to cross the wall of fire. In 1977, when the space agency engineers built it, they didn't even know the wall existed. The probe's mission was to study Jupiter and Saturn, then drift off into deep space as a silent monument to human curiosity. The fact that it survived is almost accidental. The probe's hull is made of aluminum and other lightweight metals chosen for durability and weight, not heat resistance. Its instruments are shielded, but only enough to protect against normal cosmic radiation. There's no special heat plating, no exotic materials, nothing that would suggest this machine could survive 90,000 degrees. Yet it did. And understanding why reveals something fundamental about the nature of space itself. Heat transfer requires contact. On Earth, heat moves through conduction, convection, and radiation. Conduction happens when hot particles touch cooler particles directly. Convection happens when hot fluids rise and cool fluids sink. Radiation happens when energy travels through electromagnetic waves. In the wall of fire, conduction barely happens. There simply aren't enough particles. The region is so sparse that even though individual particles are scorching hot, the chances of any particle actually hitting the spacecraft are incredibly low. Think of it like this. Imagine standing in a rainstorm where only one drop of water falls every hour. Each drop might be boiling hot, but you'd barely feel it because the drops are so rare. That's what Voyager experienced crossing the wall. Radiation was more of a concern. High-energy particles emit radiation, and radiation can damage electronics. But Voyager's designers had already shielded the probe against cosmic radiation from other sources. That shielding, though not designed for the wall, turned out to be just enough. The real danger wasn't the temperature, it was the magnetic fields. Space is full of magnetic fields. They're created by moving charged particles, and they can twist, bend, and accelerate other particles in unpredictable ways. In the heliopause, where solar and interstellar magnetic fields collide, the magnetic environment becomes chaotic. Charged particles spiral along magnetic field lines like beads on a wire. When field lines cross or reconnect, particles can be flung in random directions at tremendous speeds. It's like being caught in a cosmic whirlpool where the rules of physics seem to break down. Voyager 1's magnetometer, an instrument that measures magnetic fields, recorded wild fluctuations as the probe crossed the boundary. The field strength spiked and dropped erratically, directions reversed. Polarities flipped. For weeks, the data looked like noise, like something was wrong with the instrument. But nothing was wrong. The readings were real. The heliopause was just that violent. Despite all this, Voyager kept going. Its systems stayed online. Its transmitter kept broadcasting. And as the probe pushed deeper into interstellar space, the chaos began to fade. The temperatures dropped. The magnetic turbulence calmed. The wall was behind it. Ahead lay something even stranger. A universe Voyager was never meant to explore. The wall of fire isn't a wall. It's an ocean of particles moving so fast they blur the line between matter and energy. In this region, particles aren't just drifting. They're colliding, accelerating, ionizing. When a solar wind particle slams into an interstellar particle, the impact doesn't just create heat. It strips electrons from atoms, turning neutral gas into plasma. Plasma is the fourth state of matter, a superheated soup of charged particles that conducts electricity and responds to magnetic fields. Nearly all the visible matter in the universe exists as plasma. Stars are made of plasma, nebulae are made of plasma, and the wall of fire, it's one massive plasma field where two different stellar environments crash into each other at cosmic speeds. Solar wind particles travel outward at about 900,000 miles per hour. Interstellar particles, depending on their origin, can move at similar or even faster speeds in different directions. When these flows meet, the relative velocities can exceed 1,000,000 miles per hour. At those speeds, even atoms become weapons. A single hydrogen atom moving at 1,000,000 miles per hour carries enough kinetic energy to damage spacecraft components if it hits the right spot. Voyager's hull is pockmarked with microscopic impacts from high-speed particles, though not enough to compromise the mission. But it's not just the particles themselves, it's what they do to each other. When fast-moving particles collide, they transfer energy. Some of that energy becomes heat, some becomes light, some gets converted into electromagnetic radiation that ripples outward through space. The heliopause glows, though not in visible light. It emits radiation across the electromagnetic spectrum, from radio waves to X-rays. The space agency's Chandra X-ray Observatory has actually detected this glow from Earth. By studying the X-rays emitted from the heliopause, scientists can map the shape and structure of the boundary without sending probes there. The heliopause lights up the edge of our solar system like a neon sign invisible to the naked eye. Inside this ocean of energy, things get even weirder. Particles don't just collide randomly, they organize themselves. Magnetic fields act like invisible highways, guiding charged particles along specific paths. These paths form structures, sheets, filaments, currents of plasma that flow through the heliopause like rivers through a landscape. Scientists call these structures current sheets, and they're incredibly thin, sometimes only a few miles thick, but they carry enormous amounts of energy. If you could see them, they'd look like glowing ribbons twisting and weaving through space. Voyager's instruments detected dozens of these current sheets as it crossed the boundary. Each one triggered a spike in the magnetic field readings. Each one carried a different temperature, a different particle density, a different flow direction. It was like sailing through a sea where every wave had its own rules. And somewhere in that chaos, Voyager found something no one expected. a connection. Before Voyager, scientists believed the heliopause would mark a clean break. Inside the boundary, magnetic fields would be dominated by our parent star. Outside, they'd be controlled by the interstellar medium. Two different domains, two different rulers, a clear border between them. Voyager proved them wrong. When Voyager 2 crossed the heliopause in 2018, its magnetometer recorded something shocking. The magnetic field in interstellar space wasn't random, it wasn't chaotic, it was aligned, parallel to the field inside the solar system. This shouldn't be possible. Magnetic fields from different sources don't usually line up. They twist around each other. They interfere. They create complex, tangled patterns. Finding two fields running parallel across a cosmic boundary is like finding two rivers flowing side by side in exactly the same direction without ever mixing. The space agency scientists checked the data. They ran simulations. They compared readings from Voyager 1, which had crossed 6 years earlier. Same result. The magnetic field beyond the heliopause was aligned with the field inside. But why? One theory suggests the interstellar magnetic field isn't as uniform as we thought. It might have structure, direction, purpose. Like ocean currents on Earth, the galaxy's magnetic field could flow in organized channels, and our solar system might be moving through one of those channels. Another theory proposes that our parent star's magnetic influence extends farther than the heliopause. Even though the solar wind stops at the boundary, magnetic field lines might stretch beyond it, connecting the inside and outside in ways we don't yet understand. A third possibility is even stranger. What if the heliopause isn't really a boundary at all? What if it's more like a membrane, allowing certain things to pass through while blocking others? Magnetic fields might permeate the boundary while particles bounce off it, creating a region where two systems overlap instead of separating cleanly. This discovery has profound implications. If our solar system's magnetic field connects to the interstellar field, then we're not as isolated as we thought. Influences from the galaxy could reach us more easily. Cosmic rays, high-energy particles from distant stars and exploding supernovae might follow magnetic field lines straight into our solar system. In fact, Voyager detected an increase in cosmic ray intensity after crossing the heliopause. Inside the solar bubble, our parent star's magnetic field deflects many cosmic rays, protecting the inner planets. Outside, there's no such protection. The universe bombards you with radiation from all sides. This is one of the biggest challenges for future interstellar missions. Astronauts traveling beyond the heliopause would face radiation levels far higher than anything experienced in near-Earth space. Shielding would need to be orders of magnitude stronger. Missions would need to be faster to limit exposure time, but the magnetic field discovery suggests there might be ways to navigate these hazards. If we can map the galaxy's magnetic structure, we could plot courses along field lines, using them as highways through space. We could predict where cosmic rays will be more or less intense and plan accordingly. First, though, we need to understand why the fields are aligned, and that mystery is far from solved. The heliopause isn't a sphere. For decades, scientists assumed it would be round, like a bubble. But Voyager revealed the truth. It's shaped like a teardrop. The front of the teardrop, facing the direction our solar system is moving through the galaxy, is compressed, squashed. The back stretches out into a long tail that extends billions of miles behind us. This shape is called a heliotail, and it's created by the same forces that shape the heliopause itself. Imagine driving a car through a snowstorm. Snow hits the windshield and compresses. Behind the car, a wake forms where the air is disturbed. The heliopause works the same way. As our solar system plows through the interstellar medium at 43,000 miles per hour, the front of the heliosphere gets compressed, while the back gets stretched into a tail. The space agency's Interstellar Boundary Explorer mission, a satellite that studies the heliopause from inside the solar system, has mapped this tail using particle detections. The tail stretches at least 100 billion miles behind us. It might go even farther. We don't know where it ends. Inside the tail, conditions are bizarre. The solar wind that normally flows outward from our parent star gets caught in the tail's magnetic field and flows backward. It's like a river reversing course, pulled by forces stronger than its own current. Particles trapped in the tail can spiral around magnetic field lines for years, bouncing back and forth between the front and back of the heliosphere. Some eventually escape into interstellar space. Others get pulled back into the solar system, re-entering the very bubble they left. This creates a recycling effect. Particles that leave the solar system can return, carrying information about the interstellar medium with them. By studying these particles, scientists can learn about the galaxy without leaving our cosmic neighborhood. The teardrop shape also explains why Voyager 1 and Voyager 2 crossed the heliopause at different times, even though they launched in the same year. Voyager 1 headed toward the front of the teardrop, where the boundary is closer. Voyager 2 headed toward the side, where the boundary is farther out. Their different paths meant different crossing times. But the shape does more than explain timing. It reveals how dynamic the heliopause really is. The shape isn't fixed. It changes based on solar activity. During periods of high activity, when the solar wind blows stronger, the teardrop compresses at the front and stretches at the back. During quiet periods, it expands and rounds out. This breathing motion creates waves, pressure waves that ripple through the heliopause like waves on water. Voyager's instruments have detected these waves, measuring their speed and frequency. Some travel at hundreds of miles per second. Others move slower, taking months to cross the boundary. These waves carry information. They tell us how the solar wind is changing, how the interstellar medium is responding, how the two are interacting. By studying the waves, scientists can predict when the heliopause will shift and by how much. But predicting the heliopause's behavior is one thing. Understanding what created the wall of fire in the first place is another. The wall of fire exists because of a collision, not a collision between solid objects, a collision between winds. Invisible winds made of charged particles, each carrying the momentum and energy of entire star systems. The solar wind begins deep inside our parent star. In the star's core, fusion reactions generate unimaginable heat and pressure. That pressure pushes outward, creating convection currents that churn through the star's interior. When those currents reach the surface, they release bursts of charged particles, protons and electrons, that escape into space. These particles don't just drift, they're launched, shot outward at nearly 1 million miles per hour by the star's magnetic field. The field lines act like catapults, flinging particles away from the surface with enough energy to cross the entire solar system. By the time the solar wind reaches the heliopause, it's traveled 11 billion miles. It's passed all the planets, all the asteroids, all the comets. It's thinned out, spreading over a vast area, but it's still moving fast, still carrying energy, still pushing. On the other side of the heliopause, the interstellar wind pushes back. This wind comes from everywhere, from dying stars ejecting their outer layers, from supernovae exploding and scattering debris, from molecular clouds collapsing and forming new stars. The galaxy is full of winds, all moving in different directions, all carrying particles and energy through the void. When the solar wind meets the interstellar wind, neither gives way. They're evenly matched. The solar wind's outward pressure balances the interstellar wind's inward pressure, creating a standoff. A boundary, a zone where both winds exist simultaneously, mixing and colliding in a chaotic dance. In that zone, particles don't just bump into each other, they slam. Hydrogen atoms traveling 1 million miles per hour don't gently touch. They crash with enough force to strip electrons and create plasma. The kinetic energy of the collision converts into heat, and that heat is what Voyager measured. But it's not just heat. The collision creates shock waves, When particles collide at supersonic speeds, they generate pressure waves that ripple outward through the surrounding medium. These shock waves accelerate nearby particles, heating them even further. The wall of fire isn't just the initial collision, it's the cascade of secondary collisions triggered by the first. Think of it like a car crash. The initial impact between two cars releases energy, but that energy doesn't stay localized. It radiates outward, shattering windows, denting metal, creating a chain reaction of destruction. The wall of fire works the same way. What makes it even more intense is the magnetic field. Charged particles don't move in straight lines when magnetic fields are present. They spiral, they twist, they get trapped in loops and accelerate to higher and higher speeds. The heliopause's magnetic field acts like a particle accelerator, whipping particles around at relativistic speeds until they're moving at a significant fraction of the speed of light. These ultra-high energy particles are some of the most dangerous things in space, and Voyager sailed right through them. Our solar system isn't stationary, it's moving, barreling through the galaxy at 43,000 miles per hour, dragging its protective bubble along with it. When an object moves through a medium, it creates turbulence. On Earth, boats create bow waves. Planes create sonic booms. In space, star systems create bow shocks. A bow shock forms ahead of the heliopause, where the interstellar medium first encounters our solar system's influence. Imagine the heliopause as the hull of a ship and the bow shock as the wave that forms at the ship's prow. The wave marks the point where the water first starts to part around the ship. In space, the bow shock marks the point where interstellar particles first start to slow down and compress as they encounter the solar wind. The shock isn't visible, but it's measurable. Particles passing through the bow shock heat up dramatically, sometimes reaching temperatures even higher than the wall of fire itself. The space agency's The Interstellar Boundary Explorer mission detected the bow shock from inside the solar system by measuring high-energy particles that escape the shock and travel back toward us. These particles create a faint glow in the sky, invisible to the naked eye but detectable with specialized instruments. The bow shock sits about 10 billion miles from our parent star, slightly closer than the heliopause. It's not a sharp boundary. It's a transition zone, several million miles thick, where the interstellar medium gradually slows and heats as it approaches the solar wind. Inside the bow shock, conditions are violent. Particles collide, magnetic fields tangle, shock waves propagate in all directions. It's one of the most turbulent regions in the solar system. But here's what makes it fascinating. The bow shock isn't unique to our solar system. Every star moving through the galaxy creates one. Some are bigger, some smaller, depending on the star's speed and the density of the interstellar medium it's moving through. By studying our bow shock, we're learning how other star systems interact with their galactic environments. We're discovering how stars carve out their own spaces in the galaxy, pushing back against the universe around them. The bow shock also plays a crucial role in protecting us. It deflects some of the highest energy cosmic rays, particles that could otherwise penetrate the heliopause and reach the inner solar system. Without the bow shock, radiation levels near Earth would be higher, potentially affecting satellites, astronauts, and even atmospheric chemistry. But the bow shock isn't permanent. It depends on the density of the interstellar medium. If our solar system passes through a denser region of space, the bow shock compresses and moves closer to the heliopause. If we pass through a less dense region, it expands and moves farther away. Right now, we're moving through a relatively low-density region called the local interstellar cloud. But that could change. In a few thousand years, we might enter a denser region, and the bow shock could shift dramatically. When that happens, the wall of fire could change too, and we have no idea what that might mean for life on Earth. Voyager 1 is now more than 12 billion miles from Earth. To put that in perspective, light from the probe takes over 22 hours to reach us. When the space agency sends a command to Voyager, The signal travels at the speed of light, crossing the solar system and beyond, taking nearly a full day to arrive. And then Voyager has to respond. That response takes another 22 hours to travel back. A simple conversation with Voyager takes 2 days. You can't troubleshoot in real time. You can't react quickly to problems. You send a command, wait 44 hours, and hope it worked. This delay is one of the biggest challenges in deep space exploration. It means every decision has to be made carefully. Every command has to be tested and double-checked. There's no room for error because there's no way to fix mistakes quickly. Voyager 1 is traveling at roughly 38,000 miles per hour relative to our parent star. That sounds fast, and it is by human standards. But in cosmic terms, it's glacial. At this speed, it would take Voyager over 70,000 years to reach the nearest star system, Proxima Centauri, which is about 4 light-years away. The probe isn't headed toward Proxima Centauri, though. It's headed toward a star called AC plus 79, 3888, a red dwarf in the constellation Camelopardalis. Voyager 1 will pass within about 1.6 light-years of that star in roughly 40,000 years. By then, the probe will be long dead. Its plutonium power source, which generates electricity by converting the heat from radioactive decay, is already running low. The space agency estimates that Voyager 1 will run out of power completely by 2025 or 2030. After that, it will go silent. No more data, no more transmissions, just a dark, inert piece of metal drifting through the void. But even in death, Voyager will carry a message. Attached to the probe is the Golden Record, a 12-inch gold-plated copper disc containing sounds and images from Earth, music, greetings in 55 languages, pictures of people, animals, landscapes, diagrams showing our location in the galaxy. The Golden Record is a time capsule, a message to whoever or whatever might find it billions of years from now, long after humanity is gone. It says, "We were here. We existed. We looked up at the stars and wondered." The chances of anyone finding the Golden Record are vanishingly small. Space is vast. The probe is tiny, and it's not headed toward any particular destination. It's just drifting, one speck of dust among trillions. But the act of sending it matters. It's a declaration, a statement of hope, an acknowledgement that we're not just trying to understand the universe, we're trying to be part of it. Voyager 1 has already traveled farther than any human-made object in history, farther than the pioneers, farther than New Horizons, farther than anything we've ever built, and it's still going, still sending data, still crossing into the unknown. Voyager wasn't built to last this long. When the space agency launched it in 1977, the mission was supposed to last 5 years, maybe 10 if they were lucky. No one imagined it would still be operating nearly 50 years later. The probe's power comes from radioisotope thermoelectric generators, or radioisotope thermoelectric generators. These devices use plutonium-238, a radioactive isotope that decays over time, releasing heat. That heat is converted into electricity using thermocouples, which generate voltage when one side is hotter than the other. When Voyager launched, its 3 radioisotope thermoelectric generators produced about 470 watts of power. That's about as much as a desktop computer, enough to run all the probe's instruments, cameras, transmitter, and heaters. But plutonium-238 decays. Every year, the radioisotope thermoelectric generators produce a little less power. The decay is predictable, following a half-life of 87.7 years. By now, nearly half a century later, Voyager's power output has dropped to around 220 watts, less than half of what it started with. And it's still dropping. Every year, Voyager loses about 4 watts of power. When you're running on 220 watts total, every watt counts. the space agency has been managing this decline carefully. Over the years, they've shut down instruments to conserve power. The cameras were turned off in 1990 after Voyager completed its planetary flybys. The ultraviolet spectrometer went dark in 2003. The plasma wave subsystem was shut down in 2007. Each shutdown brought a few more watts, a few more years of operation, but eventually, there's nothing left to shut down. The probe needs power for its transmitter, or we lose contact. It needs power for its heaters, or the electronics freeze and fail. It needs power for its attitude control system, or it can't keep its antenna pointed at Earth. The space agency estimates that Voyager will cross the critical power threshold sometime between 2025 and 2030. When that happens, the team will have to make a choice. Which instruments get shut down first? Which ones stay on until the very end? The leading candidate for the final instrument is the magnetometer. It measures magnetic fields, and it's one of the few instruments still providing unique data from interstellar space. If Voyager can keep transmitting magnetometer readings until the power runs out completely, scientists will have a continuous record of the magnetic environment from the heliopause to wherever the probe is when it dies. But keeping the magnetometer on means sacrificing something else. Maybe the particle detectors, maybe the cosmic ray instrument. Every choice is a trade-off. In 2023, the space agency had to make one of those trade-offs. A thruster system that had been dormant for 42 years needed to be reactivated to keep Voyager's antenna pointed at Earth. Engineers dug into ancient documentation, studied schematics written on paper, and figured out how to fire thrusters that hadn't been used since 1980. It worked. Voyager adjusted its orientation. The mission continued. But these fixes are temporary. Eventually, the power will run out. The transmissions will stop, and Voyager will go silent forever. Before Voyager left Earth, Carl Sagan led a team to create a message. Not for us, for them, whoever them might be. The golden record was the result. A 12-inch disc, gold-plated to protect it from cosmic radiation, containing 116 images and 90 minutes of audio. Greetings in 55 languages, music from Bach to Chuck Berry, sounds of thunder, wind, whales, laughter, a mother's kiss. There's a diagram on the record's cover showing where Earth is located relative to 14 pulsars, rapidly spinning neutron stars that emit radio pulses at precise intervals. Pulsars are like cosmic lighthouses, and their pulse rates are unique. Any civilization advanced enough to intercept Voyager could use the pulsar map to trace the probe back to its origin. There's also a diagram showing how to play the record, a stylus, a turntable, instructions for converting the grooves into images and sound. The record was designed to be as universal as possible, assuming only that whoever finds it understands basic physics. But will anyone ever find it? The odds are not good. Space is unimaginably vast. Voyager is tiny. It's moving at 38,000 miles per hour, which sounds fast but is a crawl compared to cosmic distances. The probe won't come close to another star system for tens of thousands of years. Even if it does pass near a star, there's no guarantee anyone will notice. Voyager is cold, dark. It doesn't emit light or heat. It's nearly invisible against the backdrop of space. A civilization would need extremely sensitive instruments to detect it, and they'd need to be looking in the right place at the right time. And even if they find it, they'd need to recognize it as artificial. Voyager doesn't look like much. A metal box with antennas, no obvious signs of intelligence. An alien species might mistake it for natural debris, a chunk of rock or ice drifting through the void. But if they do recognize it, if they do figure out how to play the record, what will they think? They'll hear greetings. Hello from the children of planet Earth. They'll see images of humans, animals, cities, landscapes. They'll hear music that spans centuries and continents. They'll learn that we're diverse, that we care about art, that we wanted to reach out, and they'll know we're gone. Because by the time anyone finds Voyager, billions of years will have passed. Our parent star will have exhausted its fuel and expanded into a red giant, swallowing the inner planets. Earth will be a cinder. Humanity, if we still exist, will be unrecognizable. The golden record is a message in a bottle thrown into an ocean of stars. It says, "We were here. We looked up. We tried." It's one of the most hopeful things we've ever done, and it's drifting farther away every second. Voyager 1 is now beyond the wall of fire, beyond the heliopause, beyond everything we know. It's in interstellar space, the true deep, and it's carrying a piece of us with it, a reminder that we existed, a hope that someone, someday, will know we tried. Interstellar space is not empty. That's the first thing Voyager taught us after crossing the wall. We imagine space as a void, a perfect vacuum, but it's not. It's full of stuff. Gas, dust, plasma, particles, magnetic fields, radiation. The density is low, far lower than anything we'd call a vacuum on Earth, but it's there. On average, interstellar space contains about 1 atom per cubic centimeter. For comparison, Earth's atmosphere at sea level contains about 10 to the 19th atoms per cubic centimeter. Space is empty by our standards, but it's not nothing. Those atoms matter. They interact with Voyager. They create drag, enough to slow the probe down over millions of years. Eventually, Voyager's speed will decrease as it plows through the interstellar medium, losing momentum to countless tiny collisions. The gas in interstellar space is mostly hydrogen, with some helium and traces of heavier elements. It's left over from the Big Bang, mixed with material ejected by dying stars. This gas forms clouds, some dense enough to collapse and form new stars, others so diffuse they're barely detectable. Voyager is currently passing through one of these clouds, the local interstellar cloud. It's a relatively warm region, about 7,000 Kelvin, heated by shocks from nearby supernovae. The cloud is also relatively dense by interstellar standards, containing about 0.3 of an atom per cubic centimeter. But interstellar space isn't uniform. Density varies, temperature varies, magnetic field strength varies. In some regions, the density drops to 0.01 atoms per cubic centimeter. In others, it rises to 10 or more. Voyager is sampling this variability, measuring how the interstellar medium changes as the probe moves through it. One of the strangest things Voyager has found is cosmic rays, high-energy particles, mostly protons, traveling at nearly the speed of light. Inside the solar system, our parent star's magnetic field deflects many of these particles, protecting the inner planets. Outside the heliopause, there's no protection. Cosmic rays bombard the probe from all directions. Where do these cosmic rays come from? Supernovae, mostly. When massive stars explode, they release enormous amounts of energy, enough to accelerate particles to relativistic speeds. These particles then travel through the galaxy for millions of years, bouncing off magnetic fields, spiraling along field lines, until they eventually hit something. Voyager measures cosmic rays using its low-energy charged particle instrument. The data show that cosmic ray intensity increases steadily as the probe moves deeper into interstellar space, confirming that the solar system does provide some shielding. But cosmic rays aren't the only thing hitting Voyager. There's also something called the anomalous cosmic ray component. These are particles that originate at the heliopause itself, accelerated by the shock where solar and interstellar winds collide. They're lower energy than true cosmic rays, but still dangerous. Interstellar space is hostile. Radiation is intense. Temperatures fluctuate wildly depending on local conditions. Magnetic fields can trap and accelerate particles to deadly speeds. It's not a place where humans could survive without massive shielding. And Voyager is out there, alone, sending back data about a realm we can barely imagine, a realm we've never touched, a realm we're only beginning to understand. Cosmic rays are killers, not immediately, not dramatically, but slowly, insidiously, they destroy. They penetrate metal. They ionize atoms. They damage genetic material. They corrupt electronics. And in interstellar space, there's nowhere to hide from them. A single high-energy cosmic ray can pass through several feet of solid material without slowing down. These particles carry so much energy that when they hit an atom, they can shatter it, creating a cascade of secondary particles that spread out like shrapnel. In Earth's atmosphere, cosmic rays collide with air molecules, creating particle showers that rain down on the surface. We're constantly bombarded, but the atmosphere absorbs most of the energy. By the time the particles reach the ground, they're relatively harmless. In space, there's no atmosphere, no protection. A cosmic ray hits you at full strength. If you're in a spacecraft with thin walls, the particle passes right through. If it hits your body, it damages cells. If it hits critical electronics, it can cause malfunctions or permanent failures. Voyager's electronics have been hit thousands of times by cosmic rays. Most of those hits cause no harm. The particle passes through without interacting. But occasionally, a cosmic ray strikes a sensitive component. A memory bit flips. A sensor gives a false reading. A circuit temporarily shorts. The space agency engineers designed Voyager with this in mind. Critical systems have redundancy. Memory is error-checked. Software includes routines to detect and correct bit flips. But the radiation is relentless. Over decades, the cumulative damage adds up. For future interstellar missions, radiation is one of the biggest obstacles. Astronauts traveling beyond the heliopause would face cosmic ray doses far higher than anything experienced in near-Earth orbit. Current shielding materials aren't good enough. Aluminum, the most common spacecraft material, actually makes the problem worse. When cosmic rays hit aluminum, they create secondary particles that increase the radiation dose. Better materials exist. Polyethylene, a type of plastic, is more effective at stopping cosmic rays because it's rich in hydrogen, which absorbs energy more efficiently than metal. But polyethylene is weak structurally. You can't build a spacecraft hull out of it. One proposed solution is to use water or liquid hydrogen as shielding. Water is dense, hydrogen-rich, and effective at stopping radiation. Spacecraft could carry large tanks of water positioned around crew quarters to absorb cosmic rays. The water could also serve as a propellant or life support resource, making it a multi-purpose solution. Another approach is electromagnetic shielding. Instead of blocking particles with matter, you deflect them with magnetic fields. This is how Earth protects itself. Our planet's magnetic field channels cosmic rays toward the poles, creating the auroras. A spacecraft could generate its own magnetic field, creating a protective bubble similar to Earth's magnetosphere. But electromagnetic shielding requires enormous amounts of power. The magnets have to be strong enough to deflect particles moving at 90% the speed of light. That's not easy. Current technology isn't there yet. Until we solve the radiation problem, crewed interstellar missions remain science fiction. Voyager can survive because it's a robot. It doesn't need life support. It doesn't care about radiation beyond what damages its electronics. Humans aren't so resilient. Behind our solar system, stretching for billions of miles, is a tail, the heliotail, a stream of solar wind particles dragged along as our system plows through the galaxy. The heliotail forms because the solar wind doesn't just stop at the heliopause. Some particles escape into interstellar space, but others get caught in the magnetic field and pulled backward. They flow down the tail like water flowing downstream, carried by forces they can't resist. The space agency's the Interstellar Boundary Explorer mission has detected particles from the heliotail bouncing back toward the inner solar system. These returning particles provide clues about the tail's structure and composition. They're mostly neutral atoms, hydrogen and helium, that have lost their charge through interactions with the interstellar medium. The heliotail is shaped by the direction our solar system is moving. We're traveling toward a region of space called the nose of the heliosphere, in the direction of the constellation Ophiuchus. The tail points in the opposite direction, toward the constellation Gemini. But the tail isn't straight. It bends, twists, fluctuates. This happens because the interstellar magnetic field isn't uniform. As the tail extends into space, it encounters regions where the field is stronger or weaker, and those variations cause the tail to curve. Think of it like a river flowing through a landscape. The river follows the path of least resistance, bending around obstacles, widening in flat areas, narrowing in valleys. The heliotail does the same thing, following the magnetic topology of the interstellar medium. Inside the tail, conditions are strange. The solar wind flows backward, but it's also mixing with interstellar particles. The boundary between the two becomes blurred. Particles from our parent star and particles from the galaxy coexist in a turbulent, chaotic region. Voyager 2, which is traveling in a different direction than Voyager 1, may eventually pass through part of the heliotail. If it does, its instruments could measure the tail's properties directly, giving scientists a better understanding of how it forms and evolves. The heliotail also has implications for other star systems. Every moving star creates a tail. By studying ours, we're learning how stars interact with their environments on galactic scales. We're seeing how stellar winds shape the space around them, creating structures that persist for millions of years. Some stars have massive heliotails, extending light years behind them. These stars are moving faster or producing stronger stellar winds. Other stars have shorter tails or no tails at all, depending on their motion and the density of their surrounding medium. Our heliotail is modest by comparison, but it's ours, a reminder that our solar system isn't isolated. It's part of the galaxy, moving through it, interacting with it, leaving a trail as it goes. And somewhere in that trail, Voyager is drifting, farther and farther from home, deeper and deeper into the unknown, carrying our message, our hope, our legacy. The heliopause is alive. It moves, it breathes, it expands and contracts based on the solar wind's strength, and the solar wind is anything but constant. Our parent star goes through cycles. Every 11 years, its magnetic field flips. North becomes south. South becomes north. During this flip, solar activity increases. Sunspots appear. Flares erupt. Coronal mass ejections hurl billions of tons of plasma into space. The solar wind intensifies, blowing harder and faster. When the solar wind strengthens, it pushes the heliopause outward. The boundary expands, sometimes by hundreds of millions of miles. Interstellar space gets pushed back. Our solar system's territory grows. Then the cycle reverses. Solar activity decreases. The wind weakens. The heliopause contracts inward. Interstellar space reclaims its territory. This breathing motion happens slowly, over years or decades, but it's measurable. Voyager's instruments detected the heliopause shifting as the probe crossed it. The boundary wasn't in the same place from one year to the next. Scientists compare this to tides. Just as Earth's oceans rise and fall with the moon's gravity, the heliopause rises and falls with the solar wind's pressure. But unlike tides, which are predictable, the heliopause's motion is harder to forecast because solar activity is chaotic. Coronal mass ejections, in particular, create massive disturbances. When billions of tons of plasma slam into the heliopause, they create shock waves that ripple through the boundary. These waves travel outward into interstellar space and inward toward the solar system, carrying energy and momentum. Voyager has detected several of these shock waves. Each one registers as a sudden spike in particle density and magnetic field strength. The waves move fast, sometimes reaching speeds of several hundred miles per second. One wave, triggered by a massive coronal mass ejection in 2012, took 13 months to reach Voyager 1. When it arrived, it caused the plasma density around the probe to double temporarily. The wave passed, and density returned to normal. But the event confirmed that disturbances from our parent star can reach deep into interstellar space. This has implications for future missions. If we send spacecraft beyond the heliopause, they'll need to account for these waves. The waves carry radiation and high-energy particles that could damage electronics or interfere with communications. Mission planners will need to predict when waves might arrive and take precautions. But predicting solar activity is difficult. We can forecast general trends, like the 11-year cycle, but individual events like coronal mass ejections are harder to anticipate. They happen with little warning, and their effects propagate through the solar system over weeks or months. The heliopause's shifting nature also means that future probes might cross it at different locations or different times than Voyager did. The boundary won't be where we expect it. It'll be somewhere else, shifted by solar winds we can't predict. This makes interstellar navigation challenging. You can't just plot a straight course and assume the boundary will be in the same place when you arrive. You have to adapt, adjust, respond to a universe that's constantly changing. In 2012, just before Voyager 1 crossed the heliopause, it entered a strange region, a place where particles behaved unlike anything scientists had seen before. They called it the magnetic highway. The highway is a narrow region just inside the heliopause, where solar and interstellar magnetic fields connect. Field lines from our parent star link up with field lines from the galaxy, creating a bridge. Particles from interstellar space can flow along this bridge into the solar system, while solar particles flow outward into the galaxy. It's like a cosmic exchange program. Particles swap places, traveling along magnetic field lines that span the boundary between two domains. Voyager 1 spent several months in the magnetic highway before finally crossing into interstellar space. During that time, its instruments recorded a dramatic increase in cosmic rays entering the solar system and a corresponding decrease in solar particles leaving. The highway's existence was a surprise. Scientists didn't predict it. They expected a clean break, a clear separation between solar and interstellar space. Instead, they found a transition zone where the two mix and interact. This discovery has changed how scientists think about the heliopause. It's not a wall. It's not even a simple boundary. It's a complex interface where two systems exchange energy, particles, and momentum. It's a meeting place, not a dividing line. The magnetic highway also explains some puzzling observations. For years, scientists had detected anomalous cosmic rays, particles that seemed to come from the direction of the heliopause but didn't match the energy profile of true interstellar cosmic rays. These particles were accelerated in the highway, heated by magnetic reconnection events where field lines broke and rejoined, releasing energy. Magnetic reconnection is one of the most violent processes in plasma physics. When field lines reconnect, they snap like rubber bands, flinging particles to high speeds. This happens all the time in the highway, creating a constant stream of energetic particles flowing in both directions. The highway is also dynamic. Its width and location change based on solar activity. During periods of high activity, the highway expands. During quiet periods, it shrinks. Voyager's path through the highway was relatively brief, but future probes might spend longer there depending on their trajectory and the solar cycle. Understanding the highway is crucial for future missions. If astronauts travel beyond the heliopause, they'll need to cross the highway. That means exposure to elevated radiation levels and unpredictable particle fluxes. Shielding will need to account for this. The highway also raises questions. How far does it extend along the heliopause? Is it everywhere, or only in certain regions? Do other star systems have similar highways? If so, what does that tell us about the interaction between stellar and interstellar environments? These questions are unanswered. Voyager gave us a glimpse, a snapshot of one small section of the highway. But the heliopause is vast, billions of miles across, and Voyager sampled only a tiny fraction of it. There's so much more to learn, so much more to explore, and Voyager is still out there, moving deeper into the galaxy, recording data, sending signals, showing us what lies beyond. After Voyager 1 crossed the wall of fire, something changed. The temperature plummeted, not slowly. Suddenly, within weeks, readings dropped from tens of thousands of Kelvin to a few thousand. This drop confirmed that Voyager had exited the heliopause and entered true interstellar space. The wall of fire exists only at the boundary, where solar and interstellar winds collide. Beyond that zone, conditions calm, temperatures stabilize, the chaos fades. But calm is relative. Interstellar space is still hostile. Temperatures fluctuate based on local conditions. In some regions, the interstellar medium is heated by nearby stars or supernova remnants. In others, it cools in the absence of energy sources. Voyager 1 is currently passing through a relatively cool region. Temperatures hover around 7,000 Kelvin, significantly lower than the wall but still far hotter than anything we'd call cold. 7,000 Kelvin is about half the temperature of our parent star's surface. It's hot enough to ionize most gases, turning them into plasma. But because the density is so low, the heat doesn't transfer effectively. Voyager doesn't feel the temperature the way it would in a denser environment. The temperature drop also revealed something about the structure of the heliopause. The wall of fire isn't uniform, it has layers. The outermost layer, where Voyager first detected high temperatures, is the most intense. Deeper in, toward the center of the boundary, temperatures decrease. The innermost layer, just before interstellar space, is cooler but still significantly hotter than the surrounding regions. This layered structure suggests that the collision between solar and interstellar winds creates multiple shock fronts, each with its own temperature and particle density. Voyager crossed all these layers, measuring each one as it passed through. The data showed that the transition isn't smooth. Temperatures don't drop gradually. They spike and fall erratically, reflecting the turbulent nature of the boundary. Some layers are thicker than others. Some are more stable. The heliopause is a chaotic, dynamic region, and Voyager's measurements captured that complexity. Interestingly, Voyager 2, which crossed the heliopause 6 years later, recorded slightly different temperatures. The wall was cooler during Voyager 2's crossing, likely due to decreased solar activity. This confirms that the heliopause's properties change over time, influenced by the solar cycle. The temperature data also has implications for future missions. If spacecraft need to cross the heliopause, they'll experience these temperature spikes. While the low density means the heat won't damage the spacecraft, it could affect sensitive instruments. Temperature sensors, in particular, might give false readings if they're not calibrated for such extreme conditions. And there's another concern. The temperature spikes are correlated with particle density spikes. When temperatures rise, so does the number of high-energy particles. This means crossing the wall of fire exposes spacecraft to intense radiation, even if only briefly. For robotic missions, this is manageable. For crewed missions, it's a serious hazard. The wall of fire is a barrier we can cross with machines. But whether humans can cross it safely remains an open question. One Voyager has started to answer, but hasn't finished. Voyager carries several instruments designed to measure particles. These detectors are small, about the size of a toaster, but they're incredibly sensitive. They can detect individual particles, measuring their charge, speed, and energy with precision. The low-energy charged particle instrument measures ions and electrons with energies between about 10 and 100 million electron volts. It's designed to study the solar wind and how it changes as the probe moves through different regions of space. The cosmic ray subsystem measures higher energy particles, mostly protons, with energies up to several hundred million electron volts. These are the cosmic rays, particles accelerated to near light speed by supernovae and other violent cosmic events. As Voyager 1 approached the heliopause, both instruments detected dramatic changes. Solar wind particles, which had dominated the readings for decades, began to decrease. Cosmic ray intensity increased. The transition was gradual at first, then rapid as the probe entered the wall of fire. Inside the wall, particle fluxes became chaotic. The detectors recorded huge spikes in both solar and interstellar particles, reflecting the turbulent mixing zone where two winds collide. Some particles were accelerated to even higher energies by magnetic reconnection events, creating bursts of radiation that lasted for hours or days. Then Voyager crossed into interstellar space, and the readings stabilized. Solar particles nearly disappeared. Cosmic rays dominated. The flux was steady, with only minor fluctuations. This data confirmed what scientists had suspected. The heliopause acts as a filter. It blocks most solar particles from escaping into the galaxy, while allowing cosmic rays to penetrate inward. The boundary isn't perfect. Some particles leak through, but it's effective enough to create a measurable difference between the two regions. The particle detectors also revealed something unexpected. Even in interstellar space, Voyager occasionally detects bursts of solar particles. These bursts are triggered by shock waves from coronal mass ejections. The waves travel through the heliopause, carrying solar particles deep into interstellar space before dissipating. This means the heliopause isn't a complete barrier. It's porous, permeable. Disturbances from our parent star can reach interstellar space, and disturbances from the galaxy can reach the solar system. The boundary is more like a membrane than a wall. The particle data has also helped scientists understand the source of cosmic rays. By measuring how cosmic ray intensity changes with distance from the heliopause, researchers can estimate where these particles originate. Most come from distant supernovae, but some are accelerated locally, at the heliopause itself, by the collision between solar and interstellar winds. These locally accelerated particles, called anomalous cosmic rays, are less energetic than true cosmic rays, but still dangerous. They contribute to the radiation environment in the outer solar system, affecting satellites, spacecraft, and potentially future astronauts. Voyager's particle detectors are still working. They're still measuring, still sending data back to Earth, and every measurement adds to our understanding of the boundary between our solar system and the galaxy. But the detectors won't last forever. When Voyager's power runs out, they'll go silent, and we'll lose our eyes on the edge. When Voyager's power finally fails, the space agency will have to choose which instruments stay on until the end. It's a decision no one wants to make, but it's inevitable. The leading candidate is the magnetometer. This instrument measures magnetic fields, and it's providing some of the most valuable data from interstellar space. Magnetic fields are invisible, but they shape the structure of the galaxy. They guide cosmic rays. They influence star formation. They control the motion of charged particles across vast distances. By keeping the magnetometer on, scientists can continue mapping the magnetic environment beyond the heliopause. This data is irreplaceable. No other spacecraft has crossed into interstellar space. No other mission is planned for decades. If Voyager's magnetometer shuts down, we lose our only window into this region. But the magnetometer isn't the only important instrument. The plasma wave subsystem measures electromagnetic waves generated by particle interactions. These waves carry information about the density and temperature of the surrounding plasma. They reveal turbulence, shock waves, and other dynamic processes. The cosmic ray subsystem is also critical. It measures high-energy particles and helps us understand where cosmic rays come from and how they're accelerated. Losing this instrument would leave a major gap in our knowledge. Then there's the low-energy charged particle instrument, which measures solar and interstellar particles. It's been tracking the transition from solar-dominated to cosmic ray-dominated space, and its data has been central to understanding the heliopause. The space agency will likely prioritize instruments based on scientific value and power consumption. The magnetometer uses very little power, so it's a strong candidate to stay on. Other instruments draw more power and might be shut down first. But it's not just about science. There's also sentiment. These instruments have been operating for nearly 50 years. They've sent back data from Jupiter, Saturn, Uranus, Neptune, and now interstellar space. Shutting them down feels like saying goodbye to an old friend. Engineers who worked on Voyager in the 1970s are now retired. Some have passed away. The current team inherited the mission from their predecessors, and they feel a responsibility to keep it going as long as possible. Every decision is made carefully. Every watt of power is allocated with precision. The team reviews data from the spacecraft daily, looking for signs of trouble, optimizing power usage, planning for the future. But the future is limited. In 5 years, maybe 10, Voyager will go silent. The transmissions will stop, the data will end, and the probe will drift on, alone, in the dark. When that happens, Voyager will still be traveling. It'll still be crossing interstellar space. It'll still be carrying the golden record, our message to the stars. But we won't hear from it anymore. We won't know where it is or what it's experiencing. It'll be lost to us, even though it's still out there. A silent monument to human curiosity. A testament to what we can achieve when we look up and wonder. And a reminder that some journeys don't have endings, only farewells. The wall of fire is a problem for robots. For humans, it's a death sentence. 90,000 degrees Fahrenheit. Radiation levels thousands of times higher than anything we experience on Earth. Magnetic fields strong enough to rip electrons from atoms. No human could survive these conditions with current technology. A spacecraft carrying astronauts would need shielding far thicker than anything we've built. Water tanks, lead layers, polyethylene barriers. Even with all that, the radiation dose would be enormous. Cosmic rays would penetrate the hull, damaging genetic material, increasing cancer risk, potentially causing acute radiation sickness. And that's just the crossing. Spending time in interstellar space would be even worse. Without the heliopause to shield us, cosmic rays would bombard the spacecraft constantly. Astronauts would need to live inside heavily shielded compartments, venturing out only when absolutely necessary. The psychological toll would be immense. Interstellar space is dark, empty, isolated. The nearest star is over 4 light-years away. Communication with Earth would take years. You couldn't have a conversation. You couldn't ask for help. You'd be on your own, farther from home than any human has ever been. And there's the time problem. Even at Voyager's speed, 38,000 miles per hour, it would take 70,000 years to reach the nearest star. No human could survive that journey. We'd need faster propulsion, much faster. Nuclear propulsion is one option. By using nuclear reactions to heat propellant, we could achieve speeds far beyond chemical rockets. Some designs suggest we could reach 10% the speed of light, cutting the journey time to neighboring stars down to a few decades. But 10% the speed of light is still incredibly fast. At that speed, hitting even a tiny particle would release enormous energy. A grain of sand, traveling at you at 10% light speed, carries the kinetic energy of a hand grenade. Shielding against such impacts would require massive, heavy structures, and we'd still have to cross the wall of fire. Even at higher speeds, the wall would subject the spacecraft to extreme conditions for weeks or months. The faster you go, the harder the particles hit. Some scientists propose alternative routes. Instead of crossing through the wall, could we go around it? The heliopause isn't spherical. It has thin spots, regions where the boundary is weaker or less intense. If we could map those regions, we might find a safer crossing point. But mapping the heliopause in detail would require multiple probes positioned at different locations, all taking measurements simultaneously. That's a mission we haven't launched yet. For now, the wall of fire remains a barrier, a line we can send machines across but not ourselves. Voyager crossed it because it had no choice. It was programmed to go straight, and straight took it through the wall. We have choices. We can plan, we can optimize, we can search for safer routes. But until we solve the radiation problem, the propulsion problem, and the shielding problem, interstellar travel remains a dream. A distant, dangerous dream that Voyager has brought a little closer to reality. The space agency is planning a mission called the Interstellar Probe. It won't launch for at least another decade, but when it does, it'll be designed specifically to study the heliopause and the regions beyond. Unlike Voyager, which was built to study planets and stumbled into interstellar space by accident, the Interstellar Probe will have one goal: reach the heliopause as fast as possible and gather data. The probe will use advanced propulsion, likely solar sails or nuclear electric engines, to achieve speeds far beyond Voyager's. Current designs suggest it could reach the heliopause in 15 to 20 years, compared to Voyager's 35. Its instruments will be more advanced: better magnetometers, more sensitive particle detectors, cameras capable of imaging the heliopause from inside and outside. The mission will answer questions Voyager couldn't, like what the heliopause looks like from different angles and how it changes over time. The Interstellar Probe will also carry technology to communicate over vast distances. Voyager's transmitter is weak, only 23 watts, about as powerful as a refrigerator light bulb. The signal takes over 22 hours to reach Earth, and it's so faint that the space agency uses massive dish antennas to receive it. The Interstellar Probe will use laser communication, which is far more efficient. Lasers can transmit data at higher rates over longer distances with less power. This means the probe could send back more information, faster, even as it travels farther from Earth. But there's a catch. Laser communication requires precise pointing. The probe has to know exactly where Earth is and aim its laser at that point. Any error, even a tiny one, and the signal misses. Voyager doesn't have this problem because its radio signal spreads out in all directions. It's less efficient, but it's easier to receive. The Interstellar Probe will need more advanced navigation and control systems to keep its laser pointed at Earth. Another mission concept, called the Breakthrough Starshot, proposes sending thousands of tiny probes to nearby stars. Each probe would be about the size of a smartphone, equipped with a light sail. A powerful laser on Earth would push the sails, accelerating the probes to 20% the speed of light. At that speed, the probes could reach Proxima Centauri, the nearest star, in about 20 years. They'd fly past, take pictures, measure magnetic fields and particle densities, then transmit the data back to Earth. The Starshot probes would cross the wall of fire in minutes, too fast for the radiation to cause significant damage. But they'd also be too small to carry heavy shielding, so they'd need to be designed to withstand the conditions. These missions are ambitious, expensive, technically challenging, but they represent the next step in our exploration of the galaxy. Voyager showed us the edge. The Interstellar Probe will study it in detail. Starshot will take us to the stars. Each mission builds on the last, pushing farther, learning more, preparing us for a future where interstellar travel isn't science fiction. It's reality. The wall of fire isn't unique to our solar system. Every star has one. Every stellar wind creates a boundary where it meets the interstellar medium, and by studying our heliopause, we're learning how these boundaries shape the galaxy. Stars don't sit still, they move. Our parent star, along with the entire solar system, is orbiting the center of the Milky Way galaxy at about 500,000 miles per hour. That motion creates the teardrop shape of the heliopause, with a compressed front and a long tail stretching behind. Other stars move at different speeds in different directions. Fast-moving stars create more compressed heliopauses. Slow-moving stars have rounder ones. Stars moving through dense regions of the interstellar medium experience more pressure and have smaller heliopauses. Stars in empty regions expand farther. Some stars produce stronger stellar winds than our parent star. These winds push the heliopause outward, creating larger protective bubbles. Other stars, particularly older, quieter stars, have weaker winds and smaller heliopauses. By studying the diversity of stellar heliopauses, scientists are building a picture of how stars interact with their environments. This has implications for planetary habitability. A strong heliopause shields planets from cosmic rays, protecting their atmospheres from being stripped away. A weak heliopause offers less protection, making it harder for planets to sustain life. Earth's atmosphere has been shaped by our parent star's heliopause. Without it, cosmic rays would bombard the atmosphere, ionizing gases, triggering chemical reactions, potentially eroding the ozone layer. Life as we know it might not have evolved without this protection. But the heliopause isn't permanent. As our parent star ages, its wind will weaken. The heliopause will contract. In a few billion years, when the star becomes a red giant, the heliopause might shrink to a fraction of its current size or disappear entirely. When that happens, Earth will be exposed to the full force of galactic radiation. The atmosphere will change, the magnetic field might weaken. Life on the surface could become impossible. This is the fate of all stars. They're born, they live, they die, and their heliopauses reflect their life cycles. Young stars have strong winds and large heliopauses. Old stars have weak winds and small heliopauses. Dead stars, like white dwarfs and neutron stars, have no stellar wind at all, no heliopause, no protection. Voyager's measurements of our heliopause are helping scientists understand this cycle. By comparing our boundary to theoretical models, researchers can estimate how other stars' heliopauses behave and how they change over time. This knowledge is crucial for finding habitable planets around other stars. We're not just looking for planets in the habitable zone, where temperatures allow liquid water. We're also considering whether the star's heliopause is strong enough to protect the planet from cosmic rays. A planet in the habitable zone of a star with a weak heliopause might not be habitable after all. The radiation would be too intense. The atmosphere would erode. Life would struggle to survive. Voyager's data is helping us refine our search, helping us understand what makes a planet truly habitable. And in doing so, it's teaching us how rare and precious Earth really is. Voyager 1 is dying, not all at once, slowly, system by system, component by component. Like a person aging, it's losing capabilities one at a time. The cameras were first to go, shut down in 1990 to conserve power. They'd completed their mission, capturing images of Jupiter, Saturn, Uranus, and Neptune. No more planets to photograph, no reason to keep them on. Then other instruments followed. The ultraviolet spectrometer in 2003, the plasma wave subsystem in 2007. Each shutdown brought a few more watts, a few more years. But the losses are accelerating. The power supply is fading. The radioisotope thermoelectric generators are running out of plutonium. Every year, the probe generates a little less electricity. Every year, the space agency has to make harder choices about what to keep and what to sacrifice. In 2023, engineers had to reactivate thrusters that hadn't fired in over 40 years. The primary thrusters were failing, losing efficiency. The backup thrusters, designed for planetary flybys, were brought online to keep the antenna pointed at Earth. It worked, The backups fired. Voyager adjusted its orientation. But the fact that the space agency had to dig into ancient systems, unused for decades, shows how close the mission is to its end. The team is preparing for the inevitable. They're documenting everything, writing down procedures, preserving knowledge. When Voyager finally falls silent, they want to make sure future engineers, if they ever build another probe like it, have access to everything learned from this mission. They're also planning the final shutdown. Which instruments go first? Which stay on until the absolute end? How do they maximize the scientific return from the probe's last days? The magnetometer is likely to be the final instrument. It's low power, scientifically valuable, and still providing unique data. If Voyager can transmit magnetometer readings until its power fails completely, scientists will have a continuous record of the magnetic environment from the heliopause to wherever the probe is when it dies. But even the magnetometer will eventually go dark. When the power drops below a critical threshold, the transmitter will fail, the signal will stop, and Voyager will drift on, silent, into the endless dark. The space agency will keep listening for a while, just in case. Maybe the probe will surprise them. Maybe a solar flare will boost the radioisotope thermoelectric generator's output somehow, giving Voyager a few more days or weeks. It's unlikely, but stranger things have happened. Eventually, though, they'll stop listening. They'll turn the antennas toward other missions. Voyager will be gone. But it won't be forgotten. The data it sent back will be studied for decades. The discoveries it made will shape our understanding of the solar system and beyond. And the golden record will continue its journey, carrying our message to the stars. Voyager 1 is dying, but its legacy will live on forever. The golden record will outlast us all. Long after Earth is gone, long after our parent star has died, the record will still be drifting through space, preserved by the cold and the vacuum. Gold doesn't corrode, it doesn't rust. In the void, protected from air and water, it can last billions of years, maybe longer. The record could survive until the end of the universe itself, a final testament to a species that looked up and wondered. But will anyone find it? The odds are infinitesimally small. The galaxy is enormous. Over 100 billion stars, trillions of planets. And Voyager is just one tiny speck, moving at a crawl compared to cosmic distances. Even if another civilization exists in our galaxy, even if they have the technology to detect Voyager, they'd need to be looking in the right place at the right time. The probe is cold, dark, invisible. It doesn't emit signals anymore. It's just a piece of metal drifting through the void. But the golden record doesn't care about odds. It exists as a statement, a declaration, an act of hope in the face of cosmic indifference. Carl Sagan understood this when he led the team that created the record. He knew the chances of anyone finding it were almost zero, but he also knew that trying mattered. That reaching out, even into the void, even with no expectation of a reply, was important. The record contains sounds. A baby crying, waves crashing, thunder rumbling, a kiss, footsteps, music from Bach, Beethoven, Chuck Berry, greetings in 55 languages, the crackling of fire, the song of a humpback whale. It contains images, humans, animals, trees, oceans, cities, genetic material, mathematical equations, the structure of atoms, diagrams of the solar system. It's a snapshot of humanity at a particular moment in time. 1977. A world just beginning to understand its place in the universe. A world full of conflict and beauty, violence and art, hope and despair. The record doesn't hide our flaws. It shows war, pollution, poverty. But it also shows what we aspire to: peace, exploration, understanding, connection. And it shows that we tried, that we built machines and sent them to the stars, that we looked out into the darkness and didn't look away. Whoever finds the golden record, if anyone ever does, will know that we existed. They'll know we had music, language, art. They'll know we cared about more than just survival. They'll know we wondered about them, too. Maybe that's enough. Maybe the act of sending the record, of putting it out there, is its own reward. Because the record isn't just for aliens. It's for us, a reminder that we're part of something bigger, that our lives, our struggles, our triumphs are worth preserving, worth sharing, worth sending to the stars. The golden record is humanity's message to the universe, and even if no one ever reads it, the message still matters, because we sent it. Voyager 1 is now farther from Earth than any human-made object has ever been, over 12 billion miles, beyond the planets, beyond the heliopause, beyond the wall of fire. It's in a region no other spacecraft has explored, a realm we barely understand, the true edge of our solar system, where our parent star's influence fades and the galaxy takes over. This is the frontier, the boundary between what we know and what we don't, between the familiar and the alien, between home and the infinite unknown, and it's stranger than we imagined. Voyager's instruments are detecting phenomena that don't match our models, magnetic field strengths that fluctuate unpredictably, particle densities that spike and fall without warning, pressure waves that seem to come from nowhere. The interstellar medium isn't uniform. It's lumpy, clumpy, full of structures we didn't expect, clouds of gas, streams of plasma, currents of charged particles flowing in organized patterns. Scientists call these structures filaments, and they seem to be everywhere. They're thin, only a few light years across, but they stretch for vast distances, crisscrossing the galaxy like a web. Voyager has crossed several filaments already. Each time, the instruments detect a change in the magnetic field orientation, the particle density, the temperature. The probe is essentially sailing through an invisible landscape, mapping it one data point at a time. This landscape is shaped by forces we're only beginning to understand: magnetic fields, gravity, radiation pressure, the remnants of ancient supernovae, the birth of new stars. The galaxy is alive with activity, and the interstellar medium reflects that activity in complex, beautiful ways. Voyager is showing us this beauty, one measurement at a time, one discovery at a time, but it's also showing us how little we know. Every answer raises new questions. Every discovery reveals new mysteries. What creates the filaments? How do they form? How long do they last? What role do they play in star formation, in galactic evolution, in the structure of the universe itself? We don't know. We're guessing, theorizing, building models. But the truth is, we won't know for sure until we send more probes, until we explore more of the galaxy, until we push farther beyond the edge. And that will take time, decades, maybe centuries. The galaxy is vast, and we're slow. Our fastest spacecraft would take tens of thousands of years to reach even the nearest stars. But we're learning, we're building, we're preparing. Voyager is the first step. The interstellar probe will be the second after that. Who knows? Maybe missions to nearby star systems. Maybe probes that travel at a fraction of the speed of light. Maybe, someday, crewed missions. The edge of everything is calling us. The wall of fire is behind us. The galaxy stretches ahead, vast and mysterious and full of wonders we can't yet imagine. Voyager has shown us the way. Now it's up to us to follow. Voyager 1 will drift through the galaxy for billions of years. Long after its power fails, long after it stops transmitting, it'll keep moving. Pulled by gravity, nudged by stellar winds. Slowly, imperceptibly, it'll trace a path through the stars. In 40,000 years, it'll pass within 1.6 light years of a star called AC plus 79, 3888, a red dwarf, dim, cold, possibly with planets. Though we don't know, Voyager won't stop. It'll drift past, silent and dark, and continue on into the void. In a million years, it'll be somewhere else entirely, a different part of the galaxy, surrounded by stars we can't name, passing through regions we've never seen. And in a billion years, the galaxy will have changed. Stars will have been born and died. The Milky Way might have collided with Andromeda, merging into a single, larger galaxy. Voyager will still be out there, somewhere, drifting. It's immortal, in a way. Not because it's indestructible. It'll degrade over time. Cosmic rays will erode its hull. Micrometeorites will pit its surface. Eventually, it'll be unrecognizable, a lump of corroded metal tumbling through space. But the golden record might survive, encased in its protective cover, shielded from radiation. It could last far longer than the probe itself. And if, someday, someone finds it, if some distant civilization intercepts this ancient artifact and deciphers its message, they'll learn about us, about Earth, about a species that looked up at the stars and dreamed of reaching them. They'll hear our music, see our faces, understand that we were here, that we existed, that we tried, and maybe that's enough. Maybe knowing that Voyager is out there, carrying our message, is its own kind of immortality. Because Voyager represents the best of us, not our wars or our mistakes, but our curiosity, our hope, our refusal to accept limits. We built a machine in 1977 with technology that now seems primitive, computers less powerful than a modern smartphone, instruments cobbled together from parts that wouldn't be out of place in a museum, and we sent it to the edge of the solar system, and beyond, farther than anyone thought possible. It's still working, still transmitting, still teaching us about the universe. That's humanity at its best. That's what we're capable of when we reach beyond our limits, when we dare to explore, when we refuse to stay grounded. Voyager is a testament to that spirit, a reminder that we're explorers, that the stars aren't just something to look at, they're something to reach for. The wall of fire is behind us now. The heliopause is crossed. Voyager is in interstellar space, the true frontier, and it's sending back data that will shape our understanding for generations. But the journey isn't over. Not for Voyager, not for us. There are billions of stars out there, trillions of planets, mysteries we can't even imagine, and someday we'll go see them, because that's what explorers do. We reach for the stars, always.